Hello students, good evening. So we are in the session 10 of work, energy and power. So in this session, right, we will continue our discussion on this power calculation. Already in the previous class, right, so we have looked at how do we calculate the power, both in the instantaneous concept. So instantaneous power will be what? So if there is a force F acting on the body, and at that instant of time, if the velocity of the body is V, right, F dot V will give us what? The instantaneous power. Average power will be generally like, either we look at total work done by the total time taken. That is one way of getting what is the average power. Otherwise, generally average power will be used when we have a constant force. You have a constant force, right? So for a constant force, how do we get the average power? The force dot product with the average velocity. Because constant force does not mean that velocity will be constant, right? So these are the two ways in which we can get the power. Okay, so we have seen what will be the units of power and what will be the conversion factor, what will be the dimensional formula. All that we have covered in the previous session. So today we will just start with some questions on these power calculation. So look at this. There is a force given to us. What is the force? Component form of the vector they have given us. What is the force here? 60I plus 15J minus 3K. It is given in terms of SI unit, Newton. That is the force. And there is a velocity. What is the velocity value? 2I minus 4J plus 5K. That is also in the SI unit, meter per second. They are asking what is the instantaneous power. So what is the instantaneous power formula? It is nothing but F dot V, right? So just we have to do the dot product. What is dot product? If we are doing dot product of two vectors, right? What is the dot product? Product of the I components means 60 into 2 plus product of the J components. What is J component here? 15. Here what is it? Minus 4. Okay. Then product of the K components. Here what is it? Minus 3. Here K component is what? 5. So this is what? 120. 15 4s are 60, but there will be a minus. 5 3s are 15, but there will be a minus. Okay. So what is it? 120 minus 60 means that is 60. 60 minus 15 means how much it is? 45 watt. Because force is in the SI unit and velocity is also in the SI unit, right? So power will be coming in terms of SI unit, which is watt. Okay. So what is the answer? It's a straight question. So we just have to take the dot product. Check it up, guys. I'm sure we must get the answer for this. This is Dinesh. Hi. So we must get the answer for this. This is not such a complicated question. Okay. So in fact, we'll be lucky if we get these kind of questions in the JEE mains level. Okay. So we'll move on. We'll move on to the next question. So look at this. Sometimes, right, they will be particularly asking us the power delivered by a force. This is a different model of question. They will be particularly asking, like in this case, right, we are going to talk about what is the power delivered by the gravitational force. Like that, they will be asking us the power delivered by a specific type of force. Okay, maybe it can be gravitational force, maybe it can be spring force, or maybe it is a frictional force. Like that, they will choose a particular force and ask us what is the power delivered by it. Okay. So look at this. A ball of mass 1 kg is dropped from a tower. 1 kg ball is dropped from the tower. So if you drop it from the tower, what is going to happen? The ball is going to come down under the influence of gravity. Correct? It will be falling down under the influence of gravity. Okay. Find power of the gravitational force at t is equal to 2 seconds. Means we are dropping it, right? So if you drop it, it will keep coming down. It will keep coming down. See, what is the gravitational force means mg. Mass of the body is 1 kg and acceleration due to gravity is 10. So 1 into 10 means what? That is 10 Newton. That is the gravitational force. At t is equal to 2, if we know the velocity, right, then we can tell the power. Because this is the case of instantaneous power, right? What is the instantaneous power formula? The gravitational force taking a dot product with the velocity. See here, t is equal to 0, starting time, we are dropping it. Means what is the initial velocity? 0. Ball is dropped, means initial velocity is what? 0. In 2 seconds, how much velocity it will gain? So here in kinematics, right, we have seen these vertical straight line motion problems. Generally what we do there, we will use the sign convention, right? We will be using the sign convention. What is it? Anything upward we take it as positive, downward we take it as what? Negative. Okay, but since here it is moving downwards, right, so let us take downward as positive, upward as negative, because obviously when you drop it means it is going to only come down, it will not go up. Okay, so using the kinematics equations of motion, look at this. Initial velocity is 0. What about the acceleration? It is falling under gravity, means it will have an acceleration of g downwards, but here we are choosing downward as positive, so it will be what? 10. We want to find what is the v. Time is what? 2 seconds. What is the formula? V is equal to u plus at, right? Means u is 0, so v is equal to a into t. A is 10, t is 2. So 20 meter per second. That is the velocity. And what will be the direction? It will be downwards. At t is equal to 2 seconds. What will be the velocity of the ball? It will be 20 meter per second downwards. Now let us come to the power calculation. What is the power? F dot v. Gravitational force is down. Velocity is also down. So dot product means what? F into v into cos 0, which is 1. So what is the gravitational force value? 10 newtons into what is the velocity magnitude? 20. Both are in the SI system. Okay. So look at this, 10 into 20 is what? 200. Since everything is in the SI system, the power is going to be in terms of the SI unit. Correct. So check it, guys. So Sarayu, Ridhishri, okay, good. So you have to keep responding whether you are able to get the answers or not. I need to get the confirmation, right? Is it clear? So like this is the model of question. They will be asking power delivered by a particular force. Like this question, what we are doing, we are looking at what is the power delivered by the gravitational force. In some other question, they may ask what is the power delivered by the spring force every time, right? These kind of questions, they will be usually asking us instantaneous power. Means we have to look at what is that particular force value, do a dot product of that force with the velocity vector, whether it is the spring force or the gravitational force or the frictional force. Okay, whatever may be the force that they are asking us to find the power, we will be able to get it. Okay, so we will move on to the next question. See, in this power calculation area, right, we might even get questions where we'll have integration and differentiation concepts involved. Okay, so this is one such question. It's a very standard question. I think it has come in even some of the previous years. Okay, not remember exactly. It has come in. Definitely, it has come in the medical examinations, but it has also come in some of the engineering entrance examinations. So this idea of constant power. So what is this problem about? The problem is about the constant power. Okay. A constant power P is applied on a particle of mass m. So there is a particle of mass m on which we are applying a constant power. So this is not a concept of constant force or anything. The power given to this particle is constant. Okay. So obviously we have to assume that this is starting from rest. This object is basically starting from rest and we keep on giving the constant power to it. What is the constant power that we are giving to it? P. Then So I mean, we are going to do this question like a standard model. Find the kinetic energy, velocity and displacement of the particle as a function of time. Means it is starting from rest. Okay, if there is a force acting on it, means it will start moving in the direction of the force. There is a force, so whatever the force, whether it is a gravitation or whatever the force, right, that is delivering the power, the particle will start moving in the direction. Okay, so we assume that it is moving in the direction of the force. Now we need to find the kinetic energy, velocity and displacement as a function of time. Okay, so how the kinetic energy is going to change with respect to time, how the velocity is going to change with respect to time, how the displacement is going to change with respect to time. So we are going to get the kinetic energy value, displacement value and the velocity value as a function of time. We are going to get the functions. Okay, first, where do we start? We'll start with the kinetic energy. So if we start with kinetic energy, right, so initially we are assuming that it is at rest. Means what is the initial kinetic energy? Initial kinetic energy, since we are assuming it is starting from rest, it will be taken as what? 0. Now we are dealing with a constant power. Okay, so for a time t, what is the total work done by the power? Because it's a constant power, right? So what is the total work done? So whatever the force that is giving this constant power, right, what will be the total work done? Because there is a constant power, so power into time, right? Since there is a constant power, what will be the total work done? Power into time. So we are talking about a time t. In the time t, what will be the work done by the force, whichever is giving this constant power? It will be what? Power into time, because power is what? Work done by time, right? So work done is equal to power into time. Okay, we can straight away do it because it is a constant power. Okay, now this work done, right, as per the work-ends theorem, it is going to go into the change in kinetic energy. Here we are not dealing with any potential energy terms, etc. So whatever the work done, right, is going to go into the change in the kinetic energy. So which means what? The work done will be equal to change in kinetic energy. Means the final kinetic energy minus initial kinetic energy. Initial kinetic energy, because it is starting from rest, right? The initial kinetic energy, we will take it as 0. So look at this, we got it. What is it? The kinetic energy function. What is the kinetic energy function? Kinetic energy function is what? It will be simply P into T. So as time is increasing, the kinetic energy of the particle also will increase. How it is increasing? Proportional to time. Just we are using what? The work energy theorem. Work done by this force, whichever is giving the constant power, right? We are saying work done is equal to change in kinetic energy. So from there, because our assumption is initially it is starting from rest, so we are getting first function. What is it? The kinetic energy will be equal to P into T. So what is the conclusion? Kinetic energy is directly proportional to time. Okay, if you have kinetic energy, means we can straight away conclude about the velocity also, right? If you have kinetic energy, means we can also conclude about the velocity, because what is the kinetic energy of a particle? It is, if the velocity is v, right, kinetic energy is half mv square. What is the kinetic energy function? P into T is equal to half mv square. Just rearrange. 2 pt by m is equal to v square, means root 2 pt by m is equal to v. We are getting the second equation. What is it? The velocity. So here what is the conclusion? Velocity proportional to root t. Velocity is proportional to what? Root t. So what we are doing here, we are basically using the relation between kinetic energy and velocity, right? So if the kinetic energy is given as P into T, what is the kinetic energy of any moving particle? Half mv square, right? So using that, we will be able to tell what is the velocity function. Using that, we can tell what is the velocity function. Okay, so we are able to get kinetic energy function and velocity function. Now the next thing is what? We have to look at what is the displacement, right? So we have to conclude what is the displacement. So how we can find the displacement? because we know the velocity function. Using this, we have to, of course, find out the displacement. So how we can do it? So if you look at the particle starting from the initial position, right? We can take the initial position to be like the origin, and if it is moving along a particular direction, we can even choose the direction as what? The direction of the x-axis, like that. If it is moving in a direction, we can choose the direction as what? X-axis. So at any given time, velocity will be equal to what? The rate of change of the position, which is the x coordinate here. Okay, we are assuming that the particle is moving along a direction, and that is what we are taking as the x-axis. Now look at this. The relation is what? The velocity will be a rate of change of position, which is what? What is the velocity function? Root 2 pt by m. Okay. If you just rearrange the variables, we have x as one variable, time is the other variable. Dx is equal to what? Root 2p by m into t power half dt. Why are we separately writing t power half? Because that is a variable part. Root 2p by m is a constant. Now this term, right, if we integrate it, if we integrate this, right, we are going to get what is the, because remember, if we are starting from origin means what? We are starting from x is equal to 0. Finally, we reach a point x at time t. Time, what will be the limits? Time will be starting from 0 up to a value t, right? In that, the initial position we will take it as 0. Final position is what? X. This x represents what? The position. X represents what? The position of the particle. Okay. Now we'll just have to conclude this integration. That's it. If you conclude the integration, means we can get the answer. So check it, guys. The integration, right? Left hand side integration, the variable is what? X. Right hand side integration, what is the variable? Time. Okay. So let us see if you guys are able to get it. So left hand side, what do we have? Integral dx. Limits are 0 to x. Right hand side, integral 0 to t root 2p by m into t power half dt. Okay, so left hand side, look at it. Integral dx means what? X. We have to always substitute the limits. Okay, this is what? Final limit minus initial limit. That is the LHS side. Look at the RHS. Root 2p by m will come out. That is a constant. Integral 0 to t, t power half dt. So this is like what? Integral x power n dx. What is integral x power n dx? These are standard integration, right? What is integral x power n dx? X power n plus 1 by n plus 1. What is integral x power n dx? X power n plus 1 by n plus 1, right? So look at this, what we are going to get. Here what we will be having? So n is what? Half. So root 2p by m will be as it is. T power half plus 1 means 3 by 2. Divided by n plus 1 is again 3 by 2. Limits we have to substitute. Okay. So look at this. What do we have? Root 2p by m. 3 by 2 is there in the denominator. That will become what? The 2 will go to the numerator, right? 2 by 3. T power 3 by 2 minus 0 power 3 by 2. Final limit is t, initial limit is 0, right? That is nothing but root 2p by m. So here you see 2 by 3 is outside. We can take it inside. That will become what? 4 by 9 into t power 3 by 2. So what is this? Root 8p by 9m into t power 3 by 2. So this is the right hand side. Left hand side is what? X, right? So the position, how it is going to change with respect to time? Root 8p by 9m into t power 3 by 2. Okay, so these results you can just keep it. It's a very standard question. Okay, so the kinetic energy proportional to t. velocity proportional to t power half. Okay, because kinetic energy will be what? Square of the velocity, right? What about the position? Position will be proportional to 3 power 3 by 2. Position will be proportional to what? T power 3 by 2. Okay. So this is about the object starting from rest at say origin and driven by a force which is giving constant power. It is driven by a force which is giving what? Constant power. Okay. Maybe I'll just write down these results again so that we can copy the final results in one place. So what are the results we are having? The kinetic energy function is what? P into T. Velocity will be what? Root 2p T by m. That is the velocity function. And now we are getting the position function. What is it? Root 8p by 9m into T power 3 by 2. Okay. Now we have not talked about the force, right? We said there is a force which is able to give the constant power. If we want to know what is this force, tell me how we can get the force, because it is a force which is giving a constant power. The force value will not be constant. What is the property of the force? It is able to give a constant power. So if you want to know what is the force, right? Look at this, it is a constant power. Power is what? Force into velocity, because we are assuming it is moving in that direction. So whatever the force direction, right, the velocity also will be in the same direction. Okay, so power is equal to what? Force into velocity. Means force is what? Power by velocity. Force is what? Power by velocity. So from here we will be able to get what is the, so power is P, right, constant value. Velocity, what is the function? Root 2p T by m. This is the velocity function. Okay, so power by velocity is what? So we can just modify. If you modify means what you will have? Root p square m divided by 2pt. Okay, so what is it? The force will be what? Root pm by 2t. This is the force function. What is it? It will be what? Root pm by 2t. So just we are using that power is equal to force into velocity, because the assumption is they are in the same direction, right? Already we got the velocity function, root 2pt by m. Just to substitute, we will get what is the force function. So you can see force is not a constant, it is changing with respect to time. So not a constant force, it is changing with respect to time. Okay, the thing that is constant here is what? Power. Power delivered by the force is constant. Okay, clear guys? So now we'll go on to another segment which is about these water pumps. Okay, so we have not got questions on these water pumps much, but this is also related to, because when we look at the mechanical applications of the power, right, this water pump is a very common example. Okay, so what is a water pump? We know, I mean, no, we'll generally use water pump either to pump the water from one place to other place, or we'll pump the water from the ground to the overhead tank. Okay, so these are the two common ways of using the water pump. Okay, so we'll see how we'll deal with the power calculations in case of the water pump. Okay, so look at this. This is first scenario. Power of an electrical motor pumping water into overhead tank. Means what? From the surface. Okay, so we have here some water reservoir. We just taking the water, pumping it into the overhead tank. This is the tank. Okay, Let us consider a pump which is used to pump water to a overhead tank, height h. Where is it? It is located at a height h at a mass flow rate mu. So what is this mu means? Mass flow rate. Okay. What is mass flow rate? Mu will be what? The amount of mass that we are pumping divided by the time taken. The unit will be what? Kgs per second if you are going with the SI unit. Okay. So we need to calculate what is the, so this water cannot go like that, right? We will use, of course, pump. So there will be a pump that will be using to take the water from the level to the overhead tank. So here we need to calculate what is the electrical power of this particular pump. Okay. So what we'll do is let us consider time, because it's all related to the time, right? Let us consider time t. In this, what is the mass of the water taken into the tank? Because mass flow rate is mu, right? In a time t, how much mass we are taking means mass flow rate multiplied by time. That is equal to what? Mu into t. In a time t, how much mass we will take into the overhead tank? It will be mu into t. Mu is what? Mass flow rate. Okay. Now what is actually happening here? Understand, from the surface we are taking the water and then the water is going into the overhead tank. Initially when it is below in the reservoir or something, its velocity will not be there. Still water, right? It will not have any velocity. When it is taken into the overhead tank also, it will not have velocity. So here we don't need to discuss about the kinetic energy concept. Water is of course moving. To reach the top it is moving, but once it is going to the overhead tank, right, its velocity is becoming zero. So there is no discussion about the kinetic energy part. The only thing is what we are taking it from the surface of the earth to a height h, means the potential energy of the water is increasing. So what is the increase in potential energy of water? What is it? How much mass we are taking? Mu into t. So from the surface where the potential energy of that water will be what? Zero. It is going up to a height h, means what is the increase in potential energy? M into G into, for any mass, what is the increase in potential energy? mgh, right? So that will be what? Mu t into G into h. That is the increase in potential energy for the water. Now how is this increase in potential energy coming? Because of the work done by the pump, right? So work done by the pump. Okay, so actually you will say mechanical work. What is the exact word we should say? Mechanical work done, because that is what is the role of the pump, right? It will do mechanical work to take the water from the surface level to overhead tank. Mechanical work done by the pump is what? The change in potential energy, right? Change in potential energy or increase in potential energy. What is it? Mu into T into G into H. That is the mechanical work done by the pump. That's it. So we need to find what? The power. Power will be what in this case? Whatever is the work done by the time taken. Power is what? Work done by the time taken, right? This power, right, is also what we call as the output power. So power will be what? Work done, mechanical work done. Power will be what? The mechanical work done divided by the time taken, that is T. Okay, so what is it? Mu T GH by T. T will get cancelled. What is it? Mu GH. So this power is also called as what? As I said, output power, because that is what we are seeing in the output. Generally what we assume is these pumps, they are operating at 100% efficiency. General assumption is what? We'll take that the pumps are operating at 100% efficiency, but practically what happens? They will not work at 100% efficiency, right? The electrical motors are working because they are consuming electrical power. That is the input. So you have a pump here. What is the input for that? The electrical power. What is the output? The mechanical power that we are able to see. That is our mu gh. If it is not 100% efficiency, right, what would generally be observed is output power will be less than the input power. So there we even talk about, so maybe you can just note this one. This is the power. Okay, if it is not working at 100% efficiency, means what we'll have, we can talk about the percentage efficiency of that water pump, or the efficiency factor. So if that is the case, right, so we'll talk about an efficiency factor. So efficiency factor for the pump, right, that is generally defined as the output power by the input power. So output power is what? The mechanical power that you are getting. Input is what? The electrical power. Okay, so this is how we'll define the efficiency factor. If you multiply this with 100, means what? It becomes efficiency percentage. If you multiply by 100, means it becomes what? Percentage efficiency. Okay, so this is about the electrical motor pump that is used to take the water from the surface level to the overhead tank. Okay, then we can have the pump that will be used to take the water from one place to another place, generally on the horizontal level. Okay, so generally we will use these kind of pipes, right? So they are called as what? Hose pipe. Okay, so if you have a pump which is used to pump the water at a horizontal level, okay, so here the thing that we'll focus on is with what speed that the pump is able to make the water flow. So here, you know, the speed with which the water is flowing is what? V. Again, here also the mass flow rate, we are taking it as what? Mu. So usually when we are making the water flow from one place to other place, like, you know, agricultural field or etc., even in our houses, right, when you get a water tank, so this is the kind of pipe that they will use to make the water to come from the tank into the, you know, the reservoir, or, you know, the small, you know, tank that you have in your house. Okay, so the operating model here is we are not pumping the water into the overhead tank. It is moving from one place to other place, but the water will be now flowing with a speed. So if you look at the typical model, right, you have the reservoir here. This is a reservoir where the velocity of the water is what? 0. Okay, you put that hose pipe. Okay, so here you will have the pump. Now once the water is coming out of the pump, it will have a velocity. Once the water is coming out of the pump, it will have a velocity. Okay, so what is the velocity we are taking it as? We are taking it as what? V. Here again the mass flow rate is mu. What is the mass flow rate? Mu. So again what we'll say is let us consider time t. Let us consider that we are using the pump for a time t. Okay, then if the mass flow rate is mu, total mass of water that comes out of will be what? Mass flow rate mu into the time. So whatever the mass that is coming out of that pump is what? Mu into t. Now if you look at it, right, when this water is inside the reservoir, what is the kinetic energy? 0. When it is coming out of that hose pipe, it will have a velocity. So what is the final kinetic energy? Half into what is the mass? Mu into t into v square. Initially it does not have any kinetic energy because it is the reservoir. Finally what will be the kinetic energy? Half into its mass, mu into t into v square. Now here the kinetic energy of the water is changing. Why? Because of the work done by the pump. So what is the work done by the pump? Again here you will say what? The mechanical work done. What is it? Here there is no concept of potential energy involved. We are talking about the kinetic energy. So it will be what? Change in kinetic energy, means final value minus initial. Initial is anyway 0. So the change in kinetic energy will be what? Half into mu t into v square. Okay, so this is work done by the pump. Power means what? What will be the power? Work done by the time taken, means half mu t v square by the time. That's it. We get the answer. What is it? The power. This is also what the output power. What is the output power? Half into mu into V square. What is the output power? It is what? Half into mu into V square. Again, here also you can talk about that, the efficiency of that pump. So if the electrical power is not 100% getting converted into output power, right? There you will talk about the efficiency factor. Efficiency factor means what? Output power by input power. Okay. So this is about the electrical motor usage. One, we are using the motor to pump the water from the surface level to the overhead tank. Okay. Even there, right, you can also have another problem. Taking the water from the deep well, same concept. Either you pump the water from surface to overhead tank. Otherwise, from a deep well, you take the water to the surface. Both are same concept. Okay. Or you can use the electrical motor to pump the water from one place to other place using the hose pipe. Okay. Here you will talk about the water getting some velocity. Okay. So this is about the electrical motor and how do we calculate the power in case of these electrical motors. Maybe we can just note these formulae. So if at all we are getting some straight questions on this, right, we should be able to answer them. Okay. Now in fluid mechanics, right, we'll talk about this pressure inside a fluid. Okay, so we'll talk about pressure inside a fluid and we'll even have some laws. The Bernoulli equation, which will help us to find the pressure at various points in a fluid flow. So we'll discuss about that. But here, you know, in a fluid pipe, okay, so if say for example the pressure at a location is P, pressure is there means obviously there is a force, right? Because what is the force here? Pressure into, let us say, the area of cross section is A. Pressure into area will be what? Force. So we can even talk about what is the power by using the pressure inside the pipe flow. Okay, so how do you calculate the power here? So if you look at force, right, what is the force? Pressure into area. Now the fluid will be moving through the pipe with a velocity V. So here V is the velocity at the cross section. Now we'll study in the properties of fluid chapter that depending upon the cross section area, right? Say for example here the area is A1, the speed of that fluid is V1. Some other place the area is A2, speed is V2. Okay, so if the area of cross section is changing means the speed values also will change. Okay, so we'll talk about a relation between them. That is what we will be calling as equation of continuity. That and all we'll see later. Okay, but here let us come back to our discussion. So we need to find what is the power by using the pressure. See, if say velocity is V, right, the pressure will be acting in a direction where it is pushing the fluid. So the power, right, so what will be the power? Force into velocity, pressure into area into velocity. What is it? Power will be what? Pressure at that point into area of cross section into velocity. Okay, later, right, this area of cross section into velocity at any point in the fluid pipe, area of cross section will be having what units? Meter square. Velocity will be having what unit? Meter per second. So multiply them, what we'll get? Meter cube per second. So this will be what? Volume flow rate. So we'll talk about this when we go to the properties of fluid chapter. Okay, so the power can be also expressed as what in a fluid pipe? Power can be also expressed as what? Pressure at location, right? Pressure into volume flow rate. Okay, what is it? Pressure into volume flow rate. Either we will say pressure into area of cross section into the velocity, or we can express in terms of what? Pressure and the volume flow rate. What is the relation we see here? Power is equal to what? Pressure into the volume flow rate. Okay, so this is about the power calculations by using the pressure in a fluid pipe. Okay, next we'll come to the other important segment of the chapter, which is the collisions. Okay, so we talked about work and we talked about energy, different types of energy, the relation between them, that is what is the work energy theorem. And then we have talked a little about the power. The next segment of the chapter is understanding of this collisions, and one more similar phenomena, which is explosion. Okay, now the thing is collisions and explosion, right? So we'll just get some idea about what is the collision and what is an explosion. So collision may be between two particles, or it may be between many particles. So many particles will approach each other and they will have an interaction. This interaction is what we call as collision. Explosion is basically if you have any object like a bomb or something, it will explode to produce fragments. Typically what we observe is the fragments will fly off in different directions. When we will go to the study of explosion, there we will see what will be the relation between the velocities of these fragments. Okay, so these are the two kinds of phenomena which we will be calling as internal phenomena. Okay, internal phenomena means what? In the collision process or the explosion process, right? The forces that will be operating, that will be responsible for the phenomena, are internal forces. The forces that will be responsible, right? Like, you know, when an object is exploding, why is it exploding? Because something is happening inside the object. That is the reason why it is like a bomb, right? When you trigger it, some internal mechanism is there, the chemical reaction or whatever it is, because of it is exploding. Same way, if you have a collision, right, when two particles are colliding, means it is because, so what will be the force that will be there? It is the internal force. Internal force means what? During the collision, first object will apply a force on the second, second will apply a force on the first. These forces are what? Internal forces. That is the reason why we will call the collision and explosion as the internal phenomena. We will discuss more about it when we go to the specific part, but this is about the next segment of the chapter which we are going to discuss. Okay, so before we go into the collisions and explosion, right, let us take a look at this concept of momentum. Already we discussed about momentum, right? We said no, momentum will be, what is it? So here the momentum we are talking about is a linear momentum. If you have an object, right, what will be the linear momentum of the object? Mass of the object times its velocity, which will be a vector quantity. We have seen what will be the SI unit for this, kg meter per second. We have seen what will be the dimensional formula for this, ml t power minus 1. That and all we have covered. Why we are focusing on the momentum is because we'll see when we are discussing about the collisions or explosion, right, we will be particularly focusing on the linear momentum of the particles. We will even know what is the reason for that, the linear momentum of particles and kinetic energy of the particles. So already we know linear momentum is what? Mass into velocity. What is the magnitude? M into V. We can even relate this to kinetic energy. What is the kinetic energy? Let us say kinetic energy is K. What is the kinetic energy value? Half mv square. What is the kinetic energy value? Half mv square. So we can relate the kinetic energy and the linear momentum. In fact, there can be even questions formed on the relation between them. So look at it, how we can relate the kinetic energy and linear momentum. So if you have p square, what is p square means? M square v square. If you divide this by mass, that is what mv square. If you multiply both sides with half, what is it? Kinetic energy, right? So the relation is what? P square by 2m, that is what? Kinetic energy. So this is the formula for kinetic energy in terms of the linear momentum. You have for any object, right, the linear momentum value is given to us, we can express the kinetic energy. What is the formula for that? P square by 2m. The other way is expressing the linear momentum value in terms of kinetic energy. How it is going to come? Just rearrange it. Rearranging means what? P square is equal to 2mk. Take a square root. P is equal to what? Root 2mk. This we'll call it as the second equation. Okay. So the first equation is what? If you know the momentum, you can find the kinetic energy. What is the formula? P square by 2m is what? Kinetic energy. Second equation is what? If you know the kinetic energy, you can find the momentum. P is equal to what? Root 2mk. Okay. So while we are going to discuss about the collision and explosion phenomena, right, we'll be looking at these two properties. What are the properties? Momentum is one, linear momentum, and second is what? Kinetic energy of the particle or the object. Okay. And just to look at the relation between them for any object, right, the kinetic energy and linear momentum, they have this relation, so we can interconvert, or we can interchange. Like say, if you know the mass and the momentum, you can find kinetic energy. If you know mass and kinetic energy, we can find momentum. In fact, we will see that sometimes, not just in mechanics, but even when we go to +2 modern physics chapters, right, or even Mach division chapter, sometimes we will be required to use these conversions relating momentum to energy and energy to momentum. Energy means we're talking about the kinetic energy part. Okay. So look at this. Maybe we can expect these kind of questions just based on the relation between the kinetic energy and the linear momentum. Linear momentum of a particle is increased by two cases they are giving. First case is what? 100%. Second case, 1%. Without changing its mass. Let us say the mass of the object is what? M. Okay. Find the percentage increase in the kinetic energy in both the cases. So we have to separately look at case A and case B. Case A, mass is what? M. Okay. Initial momentum, let us say, is P. We are increasing momentum by about 100%. Means final momentum will be what? 2p, right? Why? Because 100% of P means again P only. We are increasing by 100% means what? It will be original momentum plus increase, which is P plus P, that will be 2p. That is the final momentum. Okay. Now first we'll solve the case A, then we'll go to the case B. Okay. Initial kinetic energy is what? We have the relation. What is the relation we have? The kinetic energy, let us call it as K. What is the K value? P square by 2m. That is the initial. Final kinetic energy, K dash, will be what? What is the final momentum? Okay, divide by mass is not changing. 2 square means 4. So it will be what? 4 times so initial kinetic energy is K, means what is the final kinetic energy? K dash. It is 4 times of K. They're asking us what is the percentage increase in the kinetic energy. What do you mean by percentage increase? Percentage increase means what? K dash minus K by K into 100. That's it, right? The increase in kinetic energy divided by the original kinetic energy into 100. So look at this. What is K dash value? What is K dash? K dash is what? It will be 4K, right? K dash value is how much? 4K. Okay, so just we have to substitute. Check it. So K dash is what? 4K minus K. What is the 4K minus? This is increase. Okay. We'll start discussing about the actual collisions from the next class. But before that, let us just solve this now. Find the ratio of linear momenta of two particles having mass 1 and 4. So m1 is what? 1 kg. m2 is what? 4 kg. If their kinetic energies are equal, means both have the same kinetic energy. We have to find the ratio of the linear momenta. Means what? Let us say momentum of this is P1. This is P2. What is P1? Root 2 mk. What is P2? Root 2 mk. ratio of the momenta, right? P1 by P2, what is it? Root 2k by root of 2 4s are what? 8k. K will get cancelled. 2 1s are 2 4s. So 1 by root 4, what is it? 1 by 2. The ratio of the linear momenta, right? P1 by P2 is what? 1:2. These kind of ratio based questions also can be asked. Okay. So this is about the relation between the linear momentum and the kinetic energy. And the next class, right, we will start with the actual discussion about the collisions. Okay, what is a collision? How the collision will occur? What are the different types of collisions? How do we see? Because we said we are going to focus on the momentum and energy of the particles, right? So we'll see how we can understand the change in the momentum or the change in the energy of the particles. That and all we'll start from the next class. Okay, we'll see in the next class.